Hi everyone. Today I will talking about the Intel's Nehalem microarchitecture. The title is From Pipeline to Cache Enhancement. I'm Namhoon Kim from Korea University. Let's dive right in. Before we get into the details, here's a quick outline of today's talk. I will start with the motivation and design goals, then move on to the processor overview and some pipeline basics. After that, I will go deeper into Nehalem's front end and its out of order execution and also execution units. We will also take a look at the simultaneous multithreading, the cache hierarchy, and memory access enhancements. Finally, I will wrap everything up with the short summary. The motivation of Nehalem architecture. The old front-side bus was basically tracking performance. Our cores had to share one narrow path to memory, which limited bandwidth and added latency. As core counts went up, coherency traffic only made things worse, and scaling across multiple sockets was really poor because of this led bottleneck of FSB bus. On the top of that, power efficiency was becoming critical, so Nehalem's motivation was clear. Fix the memory bottleneck, improve scalability, and balance performance with the energy efficiency. So, Nehalem had to fix some fundamental issues. First, the legacy front-side bus was a bottleneck, so Intel put the memory controller on die. Second, scalability was terrible across sockets, so quick path interconnect solved that with high bandwidth point-to-point links. Third, throughput. Out of order execution plus SMT squeezed a lot more parallelism per core. Fourth, cache efficiency. A large inclusive L3 made coherence much simpler and faster. And finally, smarter clock and power management gave performance without blowing up energy. Basically, this course reshaped Intel's architecture playbook and set the stage for the next decades. And here is the big architecture shift in Nehalem. Intel splits the design into core and on-core. The core handle execution, out of order scheduling, and SMT. The on-core integrates the memory controller, the shared L3 cache, the quick path interconnect. This modular layout solved the FSB bottleneck, enabled scalable multi-socket systems, and gave Intel a much cheaper path to improving their throughput and efficiency. Basically, this diagram is the blueprint of all modern CPUs like Skylake or Arrow Lake or some things. Yeah, so this diagram isn't just for a textbook. It's a 5-stage pipeline I actually implemented back in the undergrad. You can see the standard stages like fetch, decode, execute, memory, and write back. It's simple and clean, but as soon as you try to learn non-trivial programs on the CPUs, you can easily check the hazards like data dependencies, control hazards, and structure conflicts. That's exactly why modern processors like Nehalem's go beyond this baseline. They added deeper pipelines, smarter branch prediction, and out of order scheduling to keep the machine busy. So, this slide is both a quick review and also a reminder of why Nehalem had to evolve. I will briefly explain the Nehalem's microarchitecture from these sections. First, the front end of Nehalem processor. The front end is the stage that fetches and decodes instructions. In Nehalem, this part becomes much more advanced. Instructions are fetched from the L1 instruction cache with the instruction TLB. A sophisticated branch predictor runs in parallel, so the pipeline stays full without bubbles. Up to 6 micro instructions can be fetched per cycle, but only 4 move into the instruction queue. The decoders are split into 3 simple and 1 complex. Together, they can produce up to 4 micro-ops each cycle. Nehalem also introduced micro-op fusion. For example, a compare followed by branch can be merged into a single micro-op. That reduces pressure on the backend. Finally, the decoded micro-ops go into a larger queue, which keeps the out-of-order engine busy. Overall, the front end becomes deeper, faster, and more efficient. Now let's move on to the out-of-order execution, which is one of the most critical advances in Nehalem microarchitecture. So, instructions are decoded in program order, but they do not have to execute in that strict order. Instead, they enter the rename and allocate stage, where register renaming elements the first dependencies like write after read and write after write. Then, instructions are placed in the reorder buffer and reservation stations. Here, ready instructions can be issued to the execution units as soon as their operands are available, rather than waiting for previous instructions to finish. This allows multiple independent operations to overlap, significantly boosting instruction level parallelism. Finally, results are retired in order to maintain precise exceptions. In short, out-of-order execution is the mechanism that turns Nehalem into a high-throughput engine. And here we see the execution units in the Nehalem. Instructions issued from the unified reservation buffer. Instructions issued from the unified reservation stations are dispatched to 6 execution ports. Port 0 and 1 handles integer arithmetic floating point multiply and addition, as well as SSE operations. Port 2 is dedicated for load operations, while port 3 and 4 handle store addresses and data. Finally, port 5 supports integer ALU operations, branch execution, and floating point shuffles. This 6-port design allows Nehalem to sustain high degree of parallelism, balancing integer memory and SIMD workloads efficiently. Here we can see the concept of simultaneous multithreading, as known as SMT. On the left side, SMT is disabled. You can see that many of the execution slots are left idle when only one thread is active. On the right, SMT is enabled. 2 hardware threads share the same core resources, so when one thread is stalled, the other thread can fill those empty slots. This leads to much better utilization of the execution units and higher overall throughput. In other words, SMT helps Nehalem cores do more useful work every cycle without adding extra physical cores. Here we can see the cache hierarchy of the Nehalem microarchitecture. Each core is equipped with a private L1 cache, L1 instruction and data cache of the 32 kilobytes. And also, each core has a private unified L2 cache of 256 kilobytes. What makes Nehalem different is the addition of shared last level L3 cache, which can be has up to 8 megabytes capacity. This large inclusive L3 design simplifies coherence because it keeps track of what resides in the private caches. Together with the integrated memory controller on the on-core section, this cache hierarchy reduces the memory latencies and also improve both scalability and performance across multi-core systems. Now let's look at the memory access enhancement. Nehalem introduced a much more advanced memory subsystem. At the core level, the memory order buffer holds 48 load buffers and 32 store buffers, allowing the processor to handle many outstanding memory operations in parallel. The TLBs were expanded and organized hierarchically to support both small and large pages efficiently. Store to load forwarding was optimized, reducing latency from dependent instructions. On top of that, the integrated memory controller replaced the old frontside bus, cutting memory latency significantly. And also, the quick path interconnect enabled the fast communication with the on-core and other processors. Altogether, these enhancements allowed Nehalem to deliver much higher sustained memory throughput compared to its predecessors. So, to summarize the Nehalem microarchitecture, first, the front end is in order but has a deep fetch and decode pipeline. This helps handle complex x86 instructions more efficiently. Second, the execution engine works out of order. This allows instruction to be dynamically scheduled, improving instruction level parallelism. And third, Nehalem uses register renaming and advanced scheduling to remove force dependencies and keep the pipeline busy. Fourth, there are multiple execution ports, which means different types of operations can be processed simultaneously. Finally, the cache hierarchy is fully integrated and hierarchical. Each core has private L1 and L2 caches, and all cores share a large L3 cache, which improves both data sharing and memory access latency. Overall, Nehalem balances deep pipelines, out-of-order execution, and a scalable cache design to deliver much higher performance compared to the previous generation. This concludes my presentation on the Nehalem microarchitecture. Thank you for your attention.